Welcome user to the new chapter. In the previous chapter, we have seen working and practical implementation of artificial neural network. In this chapter, we are going to explore why and how we can use convolutional neural network for the analysis. Convolutional neural network follows the same architecture of mammalian visual system. Local connections, layering, and spatial invariance are the key structural points of CNN. Spatial invariance represents 360 view of the any type of feature. CNNs are typically used for the operations like object classification, object detection, object tracking, and image segmentation. In this chapter, we are going to see theoretical information about working of CNN and data augmentation concept. After that, we are going to see practical implementation in the MATLAB. So let us start with working of CNN, and this is the first lesson of this chapter. Computer stores images in a pixel coordinates, contains 3 values ranging intensities between 0 to 255. Imagine a simple image classifier that takes a color image of size 64 into 64. The input size of our neural network would be 64 into 64 into 3, that is 12288. As a result, we will have 12288 weights in our input layer for this basic type of image. Imagine with the input photos of 640 into 480 is not a huge quantity. Also, if we add number of hidden layers, computational time of the network will increase. That's why CNN has specially designed to perform operations on images. But we may have questioned what are the image features. Edges, colors and patterns or shapes are the key features of the images. Previously, CNN's feature engineering was done by hand. Now first let us see how the architecture of CNN will work. The convolutional layer is a first layer of CNN network and it is a main building block that handles majority of computational work. Filters or kernels are used to convert data or images. Filters are small units that we use in a sliding window to apply across the data. The second layer is activation layer, which uses the ReLU. In this stage, we use the rectifier function to increase the CNN's nonlinearity. The third layer is the pooling layer, which incorporates feature downsampling. Together, these all layers will perform feature engineering. After that, we do flattening and connect to fully connected layers. Now let us discuss each layer one by one. The first layer is convolution layer. A feature map is the name of the created third function. The use of filter or kernel on the input is known as a convolution. The filter or kernel is slide over the input image to perform convolutions. The size of the filter matrix, on the other hand, are defined by the programmer depending upon requirements. Right here we can see how convolution operation will happen. Input matrix represent input images within one channel. In this case, kernel window is 3 into 3. Kernel will move across the image with stride. In this case, kernel is moving horizontally and vertically with stride 1. To make it clear, watch this amazing animation to get how convolution calculation happens with one stride. A basic matrix multiplication or dot product is used in sliding procedure. Whenever network does backpropagation, the values in the filter matrix will be updated. We can customize the size of our feature map by adjusting kernel size, depth, stride and padding. The number of filters utilized is described by depth. Right here we can see stride 1 and stride 2 operations on image. More the stride number, less would be the size of feature map. In our discussed example, we have used no padding. No padding on input image will reduce size of feature map. Now let us see how zero padding will affect size of feature map. In zero padding, our input is surrounded by the borders of zeros. Basically, it is the same as putting a black border around an image. We can increase padding P to 2. Zero padding will maintain size of feature map to size of input image. After that, the next layer is ReLU. ReLU simply converts all negative values to 0 while leaving positive values unchanged. It will add smoothing to our existing feature map. After that, pooling layer will come into picture. Pooling, also known as subsampling or downsampling. The goal of this reduction is to reduce the amount of parameters that must be trained while keeping the most relevant characteristics. Max, average and sum are the three types of pooling technique. Max pooling will capture maximum number across the image based upon the stride and size of filter. Right here we have used 2 by 2 filter. Do remember, during operation of pooling, overlapping would not happen. This is how we can do feature engineering for existing data. So far we have conducted this much of the layers. We can also calculate size of convolved and pooled layer by using shown formulas. This is how we can calculate size of convolved feature map. In this formula, I is input dimension of the image, F is dimension of filter, S is dimension of stride, and P is a dimension of padding. Now let us see how we can calculate size of pooled image. After that, flattening operation will come into picture. Flattening will convert matrix data into row format, so data will be passed to fully connected network. For multi-classification, we use softmax at the end. The softmax function transforms the output of the fully connected layer into probabilities. The higher the probability value, the more accurate data class label is. This is how classification is carried out using convolutional neural network. This will end our video. In the next lesson, we are going to see how we can implement convolutional neural network in the MATLAB. Thank you for watching this video. Do like this video if you found it helpful. If you have any queries, post them in the comments and get in touch with us. Follow us on LinkedIn, Facebook and subscribe to our YouTube channel. Education is our future, MATLAB is our future. Happy MATLABing.